Hello you guys, how are you doing? This is Mike Johnston here, and today we're going to go over how to calculate these practice-related rate problems, and these were given out during the beginning of lecture, and when we discussed how to complete related rates, you'll see on screen now we have these beginner rated rate sets, and I've also added some instructions here which are directly from the handout that we have completed in class. These were the first 6 that I hope you made it through and attempted, and I'm going to go ahead and I'm going to do them out individually in this video so that way you guys can see how to do them and how to perform all of the steps in a way that you can get a correct answer. So I have them already outlined here and in this worksheet. So let's go ahead and start with number 1 and work our way through. So when I work through these, each one of these, I always think it's important to try to understand what we're given and how we are given information. So I like to start out with my givens. I like to start out with what we're given, and then I like to understand what is known. And a lot of times people say given or known. And when I say known, we can also say that those are part of our constants and what we want to find. So known, finds, givens, these are all synonymous. It doesn't matter which way that you so feel about identifying them, but again, anything is valid for this point. So first of all, let's think about this. This is a question in regards to a balloon, and the key here is that we realize that it's spherical in shape. So when I'm able to, I like to draw a picture. And this picture is not perfect. I'm not very good at drawing circles, but we realize that this problem is very nice because it's a nice sphere, which makes it really easy for us to work with. And we assume that spheres are three-dimensional, so there is a three-dimensional sphere here that's coming out, and it doesn't have to be this perfect when you're diagramming for a test, but sometimes it helps people understand that we're working in 3 dimensions. But we know with any sphere we're going to have a radius, and this radius we're just going to call a value of r. So we have a sphere, we have a radius, and that value is r, and I'll actually do that in red so we can see that sphere has a value r. I mean, the sphere has a radius value r. And again, this extends to any point of the sphere. So one thing we realize that we blow up a balloon, that balloon's radius is going to be changing. And as we blow more air into the balloon, the volume will get larger and larger, therefore causing the radius of the balloon to get larger and larger itself. So we don't expect that radius to be constant. So a lot of times it's important for us to understand our givens, understand what's constant, and then we can actually work our problem through based off of how we're able to manipulate our givens and our constants. So let's go ahead now and say, and keep reading. Notice here it says the radius is changing at the rate. So every time we see this term rate, we're thinking, at least I'm thinking, derivative. So we're thinking derivative. So we're thinking it's going to be a derivative. It's going to be the derivative of some variable with respect to, usually all related rates are going to be with respect to time. So we're going to say it's going to be the derivative of something with respect to time or something with respect to t. So notice here we have radius changing at the rate of 3 centimeters per second. And units are very helpful. Units are very, very helpful because they are indicative of that rate of change. So notice here we have the radius. The radius is changing at the rate. So most people might make a mistake and say that's just going to be a value of r. However, since it's going to be in rate, we know that our given, our knowns, our finds is actually going to be dr dt. So we're going to have a value of dr dt. The radius is changing with respect to time. And notice dr means the derivative of the radius with respect to time. And notice we have a unit of measure of length with respect to time. So we're going to say this is going to be 3 centimeters per second. So we have 3 centimeters per second. At what rate is the volume changing when the radius is 10 centimeters? So let's think about this. Notice here this term rate pops up again. We're seeing rate. We'll actually identify these rates in terms of red so we can see rate. Right? We see this term rate. Every time we're thinking rate, again, we're thinking derivative. But now this rate is going to be changing with respect to the volume of the sphere itself, of the balloon itself. So we're going to call that rate change dV over dt. And that's going to be changing, and we are looking for it. So that could be part of our find. So if you like to label this over here, you could say that dV over dt is what we're looking for. It is what we're looking to find. So that is what we are trying to figure out. What we try to figure out. That's the variable, the question we're trying to understand. So it depends on how you like to label this. It's your choice. And notice here it says, what is the rate of change of the volume? What is dV dt when the radius is 10 centimeters? So notice here the radius has now been held constant. We blew the balloon up to as much as we wanted it to be, and now the radius of that balloon is 10 centimeters. So this value r is actually going to be equal to a value of 10 centimeters. So this is not going to change. Even though the radius is changing dynamically as we blow the balloon up, we are looking for the rate of change of volume at the specific instant that the radius is 10 centimeters. So now let's think about how we can relate volume of a sphere, radius of a sphere, all together. So we should recognize that the volume of a sphere is going to be equal to 4/3 pi r cubed. And again, r cubed is going to be a relationship of volume. Anything that's going to be raised to the third power is usually a volume. We think of centimeters cubed or milliliters cubed. Those are going to be always volumetric measurements. So every time we see that cubic, that should be thinking volume. Notice here, if we look at this 4/3 pi, these are just constants. These are just constants. So we realize at this point that we're going to be taking derivatives. These constants should not play should not add any difficulty to our problem. A lot of times people don't recognize that the pi is constant. Pi is going to be constant. It does not change, even though it is irrational. It does not change. 4/3 is constant. It does not change. The only thing that's changing here is the volume of our sphere and the radius itself. So now let's go ahead and take our derivative. So if we take our derivative of the volume with respect to time, we're doing everything with respect to time, we're going to have the derivative of volume with respect to time. 4/3 pi, I'm just going to hold out as a constant. Again, we are taking the derivative of this equation implicitly. This is a form of implicit differentiation. And now we're going to have to take the derivative of r cubed with respect to time. So we will have the derivative of r cubed, which will just give us a value of 3r squared, times the derivative of r with respect to time, which will give us the value of dr over dt. So we have to take the derivative of r with respect to time. This is an implicit differentiation question. Now we can recognize that our 3's will cancel. So simplifying this, we have dv over dt is equal to 4 pi times r squared dr dt. Okay, let us see what we know and let's see what we don't know. Notice here, we know dr dt, that's equal to 3. We're looking for dv dt, so that's an unknown. And lastly, we have our value of r, which is 10 centimeters at the specific instant that we are evaluating the rate of change of the volume of the sphere or the balloon itself. So all we have to do now is just plug in to figure it out. So dv dt will be equal to a value of 4 pi times r, and I'm going to plug in here using my units. I never want to drop off my units with related rates because they often give us hints to make sure that we're on the right track, times dr dt, which is going to be 3 centimeters per second. So 3 centimeters per second. Simplifying this, we're going to have a value of 4 pi times 100 centimeters squared, 100 centimeters squared times 3 centimeters per second. Multiplying all this together, 4 times pi times 100 times 3 will give us 1200 pi. Centimeters squared times centimeters gives us centimeters cubed. And again, that centimeters cubed should be hinting to us that that's going to be a volume. Anything that's cubed will be a volume, but still a volume with respect to time. We're going to have that time, which will be our value of seconds, and that will be 1200 pi centimeters cubed per second. So again, there's a lot of ways that we can go about doing these problems. Most of our related rates will be forms of implicit differentiation. Let us go on to problem number 2. So here we have a ladder that's 10 feet long. It's resting against a wall, which is pretty consistent with most ladders. If the bottom of the ladder is sliding away, so notice here it's sliding away. Hopefully we're thinking if something's moving away that it is going farther from the origin. Maybe that value could be getting negative or positive, but let's go ahead and analyze it and see how it's working. And sliding away from the rate of the wall at the rate of 1 foot per second. How fast is the top of the ladder moving when the bottom of the ladder is 8 feet from the wall. Okay, so that's just a lot. There's a lot going on here. But let's go ahead and first start off with our picture. So we're going to have a picture. I'm going to assume that the wall is creating a 90-degree angle with the ground, and I'm going to have a ladder that is resting against the wall like such. And one thing I always like to identify are values that are constant. Values that are constant. And if we think about this, it says a ladder is 10 feet long. I think that we can safely assume that the ladder's length is going to be a constant value of 10 feet. That is not going to change. That ladder is not going to get any longer or shorter. So when I have a constant value, I often feel that it's safe for me to label that on the diagram itself. So I think that's fair for me to label on the diagram itself. So I'm going to go ahead and say this is 10 feet. That's not changing. So my ladder is going to be constant. If the bottom of the ladder is sliding away from the wall, so I'm going to extend my floor a little bit. So I know that this value from here to here, which I'll just identify in red, so the tip of my ladder to the origin or wherever my wall intersects the ground, I realize that as the ladder moves away, this value is going to be changing. So now take a second and think to yourself, am I going to want to label this value with a constant number, or are we going to want to use a variable? I hope you thought we're going to use a variable. Since this value is changing, it is not going to be constant. We're going to want to use a variable because that value will be getting larger and larger and larger as the ladder falls further and further towards the ground. So just to be consistent, I know that if I look at horizontal values x, my vertical values are usually y. You could have drawn this ladder to be over on this side, so you could have said you had a positive axis. For all of you that are going into physics and taking advanced physics courses, you're able to determine what the orientation of your positive x and your positive y axis. So for this sake and purpose, I'm going to say my positive x direction is going to be to the left, and I'm going to say that my positive y value is going to be to the right. So as we move further and further to the left, this will actually be getting more positive based off the orientation of my axes. It depends, again, how you draw your picture, how you interpret these values, but I like to work with positive values. So we expect my value of x to be getting larger. And in terms of the rate of change, the rate of change is also going to be a positive value because my length of x, as I move farther and farther from the origin of the intersection, will be a positive value because it's indicating my x value is larger. But now I know that this value from the tip of my ladder to the ground, I'm going to call this value a value of y. I realize that value is going to be changing as well, but hopefully we recognize this value of y is getting smaller and smaller and smaller. Therefore, if my value of y is getting smaller and smaller and smaller, I expect my rate of change of y with respect to time to be negative. This is actually a form of a vector. So just now I'm going to label some suspicions. Some suspicions. Sorry for this handwriting. It's a little tough for me sometimes. Some suspicions. I expect my rate of change of x with respect to time, I expect that to be a positive value. And I also expect my rate of y changing with respect to time to be a negative value. I expect this to be positive. The x value, I expect the length of x to be positive. It will be increasing, and I expect my value of y to be decreasing. So these are my suspicions. Again, I'm working through this step by step. So let us continue with the problem. If the bottom of the ladder is sliding away from the wall at the rate of 1 foot per second. So notice here we have that term rate again. Hopefully now when we see that term rate, we're thinking derivative with respect to time. Second is going to be that form of time. And it's going at the rate of 1 foot per second. In terms of how I labeled my graph, how I labeled my picture, that will be a value of dx over dt. Dx over dt. And since it's moving this way, I expect that to be positive based on the way I label my axes, and that will be a value of 1 foot per second. And often you can see, ft per s. S is a convention that's used to determine seconds as well. To label seconds. So that's an okay convention to use. So now it says How fast is the top of the ladder moving down when the bottom of the ladder is 8 feet from the wall? Okay, so how fast is the top? This right here is the top. How fast is the top of the ladder moving down the wall at the specific instance when the bottom of the ladder is 8 feet from the wall? So we're looking at the specific instance when the bottom portion of this ladder is 8 feet from the origin. Okay, so I hope we recognize now we're looking for how fast. Fast, again, is a term that indicates speed or velocity. We can think how fast something's going. Speed, velocity. Remember, speed is the magnitude of velocity. So we're thinking about a rate of change with respect to time. So we're going to say that we're looking for dy over dt. We're looking for how that is changing. And again, we expected this value to be negative. And at the specific instance, when the bottom of the ladder is 8 feet from the wall. So when the bottom of the ladder, we're going to call that value x, because that is a distance, is going to be 8 feet from the wall. Okay, so now we have to recognize how we can relate the length of the ladder, which is going to be this portion of our picture, the height of the ladder, and the length. So hopefully you all recognize, since we have a 90-degree angle, that we can use the Pythagorean theorem. We can use that Pythagorean theorem. And we can state that we have, I'll just use the term, a squared plus b squared is equal to c squared. That's the Pythagorean theorem. It's the length of one side of the triangle squared plus the length of the other side squared is going to equal to the length of the hypotenuse squared. So I like to plug in anything that I know to be constant. We are allowed to plug in this point anything that is constant. So we're going to plug in our constants. So we're going to plug in our constants. Notice the only constant we have here is 10. Many people make the mistake that this value of x along the horizontal portion of the ladder is constant. However, remember, this value is changing. This value, this distance, is getting larger and larger and larger. We're just looking for the specific instance when this length is 8 feet. Just like in the last problem with the balloon, we were looking at the specific instance when the radius of that balloon was 10 centimeters. So here, the only constant I can plug in is for my value of c. So I know a squared plus b squared is equal to 10 squared, which implies that a squared plus b squared is equal to 100. So now I'm going to label in terms of my pictures. I'm going to have x's, I'm going to have y's. So I will have, I'll just do it up here so we can all see it, x squared plus y squared is equal to 100. Now we're going to have to take the derivative with respect to time, implicitly working our way left to right. So we're going to have 2x times the derivative of the inside, which will be dx over dt, plus 2y dy dt, and that's going to equal the derivative of 100, and the derivative of any constant we know always to be a value of 0. So now let's see if we have everything that we need to solve. So notice dx dt is equal to 1. We know dx dt. dy dt we're looking for, so we know we can find that. And lastly, we have when x is equal to 8, we have x to be 8. However, what is a variable that we're missing? I hope we all recognize now that we're missing a value of y. So how can we go ahead and find what y is at the specific instance that our x value will be 8 and our hypotenuse is constant at 10? And I hope we all recognize that this is also a specific type of triangle that we can use, and that's, again, so if we want to find the value of y that we're given, let's go ahead and analyze a triangle at one specific instance. We took a snapshot in time, and we found at one particular point in time that this value is going to be 10. This value is going to be constant at 8 at one specific time, and this value will be y. We're going to call it y to be consistent. If we make a relationship, we know that 8 squared plus y squared is equal to 10 squared. So 8 squared plus y squared is equal to 10 squared. 64, 100, y squared will equal to 100 minus 64, which gives you 36, or y will equal to a positive 6. I know when we solve for y, when we take the square root of both sides, you're supposed to get plus or minus, but I hope we recognize this will never be a negative length, so this is why this will only have a plus value, a positive value. So now we know we have another given that was sort of hidden in our problem, that y is also equal to a value of 6 feet. So that took a little bit of initiative to figure out, but hopefully we can all understand how to do this through practice. Now we know every single term. So let's go ahead and solve and isolate in terms of our variables for what we're looking for. So we're looking for dy dt. Our 2's will cancel. Our 2's will cancel. And we're going to be left with x dx dt plus y dy dt is equal to 0. I'm going to subtract y dy dt. I'm going to subtract y dy dt, so I'm going to have y subtracting that, dy dt. It cancels over here, and I get x dx dt is equal to negative y dy dt. And again, we want to isolate for dy dt, so we're going to divide everything through by negative y, divide everything through by negative y. So I know some of us might be a little worried here about this negative, but however, remember what we hypothesized at the very beginning? That dy dt was going to be a negative value. And notice that's showing up to be consistent in our proof, in our solution. So we know that dy over dt will be plugged in. We'll have negative x divided by y, or negative x divided by positive x divided by negative y, either one. So x in our circumstance will be 8, y will be 6, negative out in front will be negative 8 feet divided by 6 feet, all now times 1 foot per second. The feet here cancel, and dy dt will be equal to a value of negative 4 over 3. The feet per second from that velocity will remain. And notice we got a negative y value just like we hypothesized. So in this circumstance, this one took a little bit more initiative to figure out all the givens, even though they weren't specifically stated in the problem. We had to use our Pythagorean identity not only once to determine the related rate, but we also had to use it again to figure out the constant value at the specific time when this length of the tip of the ladder at the bottom was 8 feet from the origin. So hopefully that problem was not so bad, and again, through practice and understanding, this should become pretty easy and almost second nature. So let's go home now, and we'll bump up to something that seems a little bit more difficult. However, it's really not so bad. Let us look at the famous example of the baseball diamond. So we have a baseball diamond that's 90 square feet, and that should be pretty easy for us to understand and conceptualize. So a baseball diamond is going to be a square, and this square has lengths that are 90 feet. So this is 90 feet, and this is 90 feet. A lot of times you can use the little slash to represent feet. I know we've been bouncing back from metric to standard form, but again, that's just through practice. You're going to see these problems written in all these different types of units, and you must be comfortable with using all of them. So this is my best representation for baseball diamond, especially drawing on a notepad. So the pitcher's mound is the center of the square. So we're going to have the pitcher's mound is going to be right here at the center of the square. If the pitcher throws a baseball at 100 miles per hour, how fast is the distance between the ball and first base changing as the ball crosses home plate? Wow, that's a lot going on, and it definitely has a good amount of information just in this one sentence. So let's go ahead and try to draw a picture and see exactly what we have going on here. Well, I hope we recognize that with a square, that if I draw, that's supposed to be over there, there we go, and then I'm going to draw a line connecting the pitcher's mound to the first baseman. This is first base. I'm also going to draw a line connecting the pitcher's mound to home plate. We recognize that this length between the pitcher and first base will be a relationship because of the way that our squares are made. We recognize this is going to be a constant hypotenuse. All squares have angles that are equal to 90 degrees because we have 90 degrees times 4, which gives you 360. If we bisect our angle in half, this will be a 45-degree triangle, and this will be also a 45-degree triangle. So with a 45, 45, 90, we should all recognize that we have a very neat relationship, 45, 45, 90, that the relationship will always be 1 square roots of 2. So 1 times square root of 2. And if we know this value is going to be 90, we know that this value will also be 90 over square root of 2. And this value will also be 90 over square root of 2. So that's what this relationship is. However, we recognize that I'm going to draw a ball. I'm going to draw a ball in green. I'm going to say that it's at this point right here. So hopefully we can all see that. The pitcher threw the ball, and the ball is traveling down to home plate. And this will be home plate. And this will be first base. So that'll be home plate, and that'll be first base. So when we are analyzing this problem, we are ultimately looking for the rate of change between the ball and the first baseman, or the ball and first base. So we are looking for the rate of change of this length right there. So we are looking for the rate of change of this length right there. And as the ball travels, as we get across home plate, the length between the first baseman and the ball will be changing, but also the rate of change of that length is also a value that is going to cause the length of itself to change. So as the ball travels, this length, the distance between the ball and first baseman, will also change. So now we have to wrap all of this into a way to analyze mathematically. I know it seems like a lot, but it's not so bad. So hopefully we recognize at this point that we have one constant. This one constant can be 90 over square root of 2. The distance between the pitcher and the first baseman will not change. So my constant will be the distance between the pitcher and first base. I hope we recognize that this distance is going to be changing between the ball and the first baseman. We are analyzing the relationship between the ball and the first baseman. And notice here, I'm just going to call the value at any time between the ball and the first baseman, I'm just going to call that a value of R. I hope we all recognize as the ball gets closer and closer to the to home plate, that R is increasing ultimately till when it crosses home plate, that value R is going to be a value of 90 feet, the maximum distance between the first baseman and home plate. So we will assume that there is a 90-degree triangle that is going to be formed between the first baseman's length to the pitcher's length to first base, and the home plate will form a 90-degree angle. And I'm just going to call this value, I'll call this value Y. Why? Because we have a vertical distance that will be changing. Here's a horizontal value that will be changing. So notice here I can apply Pythagorean identity, or the Pythagorean formula, identity. We know that a squared plus b squared is equal to c squared. A squared plus b squared is equal to c squared. Notice here, if I call this value my a, that value is constant. This value, my y, will be my value of b, and my c is just my value of r. So that's all this Pythagorean idea is going to relate my 90 over root 2 to this value of y, which is getting larger and larger and larger, and then also to that value of r, which is equal to c. So placing this in, I'm going to have 90 over square root of 2, quantity squared, and this will be in terms of feet, and I have to be consistent with my units. This is feet, because this is feet, so we're going to have feet, plus b, but b is just the value of y, the distance between the ball and the pitcher at any given time as it's traveling down. So as the ball is traveling farther and farther away from the pitcher's mound, that value of y is getting larger and larger. So that is not going to be constant. We're just going to call that value of y squared. And this will equal to a value of c, and c is also changing. Many people think c is going to be 90, and that will be at the specific instance when the ball crosses the home plate. However, as the ball is traveling, that value of c, we call this r according to our pitcher, so we're going to call this a value of r squared. So now let's get a chance to simplify this and break it down a little bit. So we're going to have 90 squared, which is 1,800 feet, all over square root of 2 squared, which is just a value of 2, plus y squared is equal to r squared. 18 over 2 is just going to be 900 feet, plus y squared is equal to a value of r squared. So now we have a way for us to relate this problem of the length between the pitcher and first base and the distance between the ball and the ball and the pitcher and the ball and home plate. So now again, we're going to look at our instant snapshot. Our instant snapshot. What are we specifically analyzing? We want to find out how fast, okay, again, we're thinking fast, which is going to be a derivative. How fast is the distance between the ball and first base going? The ball and first base. The ball and first base. Notice we call that distance r. According to our picture, we call that distance r, but we're looking for the speed or the velocity of that value r. So we are actually looking for, what we are looking for is dr over dt. We are looking for the rate of change of the distance between the ball and the first base. So we are looking for the distance between the ball and the first base when the ball crosses home plate. So we're looking at it specifically, and I'm going to do that one in red at the specific instance, so we're going to do that in red. We're looking for this, when the ball crosses home plate, what is the rate of change of our value of c with respect to time? But this actually works out real well, because we know the length of c, not dc dt. I'm sorry, we call this r, not c. So we're going to have r, we called it r. So our length r will be equal to 90 feet. Because it's that specific instance, the snapshot when the ball crosses the home plate. So our radius is going to be 90 feet at the time that the ball crosses the home plate. Our value of y, which is the distance from the pitcher to the ball at the time that it crosses, is going to be a value of 90 over square root 2. So it's going to be the value of y, which is going to be 90 all over square root 2 feet. And at that specific point, it's going to cross, it'll be 90 over square root 2 feet because of the relationship of this triangle. So now let's go ahead and take the derivative of our Pythagorean identity that we wrote in respect to this problem. The derivative of 900 feet is just going to be a constant, so that goes to 0. So we're going to have 2y times dy all over dt is equal to 2r times dr over dt. Notice I'm looking for dr dt. I have a value of r. I have a value of y. And now the question is, do I know my value of dy dt? Let's think about this. This was something given the problem, but sometimes a little bit confusing. If we look at this, our value of y dt is the relationship of the distance between the ball and the pitcher. And we know that that relationship is going to be 100, as we said before, feet per second. So we're going to go ahead and call this value dy over dt, which is 100 feet per second, just to make it easy on us. So now we know our value of dy dt. Let us go ahead and plug in and see what we get. Plugging in directly, and we could solve. We realize the 2's will cancel. That makes it a little bit easier for us. We can solve directly for dr dt. So we get y all over r, still times dy dt is equal to dr over dt. So we divided both sides by r. I'll show what that step was. Divide both sides by r. So plugging directly in now for y over r, we're going to have y, which is going to be 90 feet divided by square root 2 all over r, which is 90 feet, still times dy dt, which is 100 feet per second. And here's the reason why the time doesn't actually really matter. The units don't really matter, is because the feet over the feet cancel out. So this is going to be independent. So the feet cancel out with the feet, the 90 cancel out with the 90. So we're going to be left with 100 all over square root 2 feet per second. So that completes this problem. We realize here that the units are solely dependent upon the speed or the velocity of the ball itself, and the distance actually has a little relevance to it, however, not very much. Any questions? Let me know. Now let us move on to problem number 4. On to number 4. So two planes approach an airport, one flying due west at 120 miles per hour and the other flying due north at 150 miles per hour. Okay, so we have to draw a picture. I'm just going to put my airport right there. Airport, I have one plane that's flying due west at 120 miles per hour. Another plane flying due north at 150 miles per hour. Okay, so just to be consistent with conventions, I hope we're seeing this. I'm going to go ahead and call this value, this rate of change, which is not going to be constant because the plane is flying, I'm going to call this a value of x, and I'm going to call this value a value of y. So hopefully now we're starting to see that this will make a relationship between the two planes, and this distance will also be decreasing. So I'm going to call this a value xy. I'll just call this z. Any variable that you want. So now let us work through the givens. So we're going to work through the givens. So here we know this value of x. X is changing at 120 miles per hour. So we know that's going to be dx over dt. And this value y is changing, and that is also changing at 150 miles per hour. Not also changing, but it is changing at 150 miles per hour. So we're going to say dy dt is 150 miles per hour. But let's look at our convention. We realize that our magnitude of x is getting smaller. Therefore, this rate of change must in fact be negative. The distance between the plane and the origin, which we're going to call the airport now, is getting smaller and smaller in magnitude. Therefore, this value of dx over dt must be negative. The same thing applies here to y. Since my value and magnitude of y is getting smaller and smaller, I also know that my rate of change of y with respect to time must also be negative. So now we can continue on with our question. Assuming they fly at a constant elevation, their elevation is not changing, how fast is the distance between the planes changing? Distance between planes changing. Notice changing, we're thinking again derivative, distance between the two. According to us, that will be dz over dt. We are looking for the distance between the two planes. And again, that's going to be based off of how we labeled our initial constraints. In our initial diagram, we left this value be of z, and that could be any variable that you want. It could be a, could be t, could be r, could be p. Does not matter. But we have a specific circumstance now. We took a snapshot, and our snapshot of the planes is when the westbound plane is 180 miles from the airport, and the northbound plane is 225. So this value is just a value of x, and this value is just your value of y. So at our snapshot, we know that x is going to be equal to 180, and our y value is equal to 225. So I bet we're probably going to have to find z. If we know x and we know y at some specific circumstance, then I bet we're also going to have to be able to find z. So I bet that's what we're going to have to do. But let's go ahead and see if we can make a relationship of these two. So hopefully now we can recognize that this will be one right triangle. Relating our Pythagorean identity again, we know that x squared plus y squared is equal to z squared. And notice, nothing's constant anymore. This plane is changing, this plane is changing, and the distance and magnitude between the two planes is also changing. They're all getting negative. So we have no constants in this problem. According to us, now we're going to have to take our derivative, but we're going to do it implicitly with respect to time. So we're going to have 2x times dx over dt plus 2y times dy over dt, and that's going to equal to 2z times dz over dt. So hopefully we recognize that if we divide everything through by 2, that our 2's all cancel, and we get something that's a little bit easier to work with. Notice here we have our value of x. We have our value of x. We know dx dt. We know dx dt. We have our value of y. We know dy dt. We don't have z, and that's what I suspected we're going to have to figure out. So we're going to have to find z, and then we're looking for dz over dt. So I'm just going to, while I'm in the mood, I'm just going to solve this equation for dz dt. So I'm going to have x times dx over dt plus y times dy over dt, and I'm going to divide both sides through by a value of z, just to isolate my dz dt. So let us go ahead and use our Pythagorean identity at the specific instance. The specific instance when the distance from the westbound plane is 180 and the northbound plane is 225, and we have to find this value of z, which we called the hypotenuse, or the distance between the two. So we're going to have 225 squared plus 180 squared is equal to z squared. So we realize in this circumstance that we're going to have to solve for z. So in this circumstance, 225 squared, which will be 50625, plus 180 squared, which will be 32400, and that'll equal to z squared. Adding these two together, we should get 520399302. Oh wait, no, 83025. 1, 2, 3. Yeah, 1, 2. Yeah, 83. 1, 2, 3. Yeah, 83. I'm having a day. 83025, which will equal to a value of z squared, and that implies that z will be equal to the square root of 83025 and 83228. That will be approximately, I don't have a calculator with me, I'm doing math here, I don't have a calculator. That'll be equal to approximately 288.1 something. But again, you would have a calculator on a test, so you'd be able to approximate this value. So plugging in for dz dt, solving for dz dt, we would have x, but x in this circumstance is equal to a value of 180 miles times dx dt, and notice this is going to be a negative 120 miles per hour, negative 120 miles per hour, plus y, and y in this circumstance is 225, times dy dt, which is negative 150 miles per hour, and this will be all over a value of approximately 288.1 miles. So I don't have a calculator. I'm not going to worry about doing this. I'll let you guys do this independently. But we should get a negative value here, another negative value here, negative minus negative is negative, divided by a positive makes it negative. But we suspected dz dt to be negative because this value of z is getting smaller and smaller, and this dz dt derivative, the derivative of my value of z, is indicating that this length is getting smaller and smaller. So whatever this is a value that you would get. So hopefully we can all figure this out with a calculator. Any questions, let me know. Otherwise, we're going to move on to our last two. So this one I always like because this always reminds me of a couple of movies I saw when I was younger about, watching salt pile onto a cone, and the cone got larger and larger. So I've always enjoyed that. But let's go ahead and work this through step by step, just like we've done it before. Sand falls on an overhead bin, accumulating a conical pile, conical meaning cone, with a radius that is always 3 times its height. So here's one of these neat always. So I'm just going to draw a quick picture here, and I have a mound of sand, and it should be a cone, so it should be more pointy. So I have a mound of pointy sand. It looks like that. So notice here I have a height. I'm going to call this value of h. and then I have a radius, and my radius is going to extend anywhere between the center of my cone and the extension port, the farthest circumference of my cone. Again, this is three-dimensional. This actually is a three-dimensional picture. I'm just drawing a 2D, but this should be extending out like such. And we should have a 3D picture, but that's the best I can draw in 3D on this tablet. So notice here that we have one very important constant at the very beginning. So notice here it says that the radius is always 3 times its height. So the radius is always 3 times its height. And this is a always circumstance. That makes it very nice. So I'm just going to bump down here I'm going to skip all these numbers, and I just see that the volume of a cone is 1/3 pi r squared h. So I know the volume of my cone is 1/3 pi r squared times h. But at this point, I know r is equal to 3h. So let's take 3 seconds out and see if you can figure out what I'm going to do next. Exactly. I'm going to substitute this value of 3h in for r. So I know volume is equal to 1/3 pi r, but r I'm going to say is 3h, quantity squared times h. This will equal to 1/3 pi 9h squared, still times h. This is 9h squared, this is h. And this is going to equal to 1/3 pi times 9h cubed. And notice here, look what cancels. The 3 and the 3 gives me this. So my volume is going to be equal to 3 pi times h cubed. Notice by me working through this and understanding this constant, the r is equal to 3h, that now we've eliminated one of the variables. We no longer have a volume in terms of the radius. We only have the volume in terms of height. So hopefully we recognize this point that we're going to have to take the derivative of this thing implicitly. And if I would have left it like this, we would have had to use a product rule. And I know I did not want to use a product rule and have more variables and more derivatives to work with. Here I'm going to have just one nice, taking the derivative of h cubed with respect to t, and it works out very, very nicely. So now let's see what else we have here. So it says, if the sand falls from the bin at a rate of 12 feet cubed per minute. Okay, some people might get confused with this, but it's okay. But notice here, what is this rate? Feet cubed. I hope we're all thinking this is a volume. Every time you see something cubed, that's going to be a volume. So let's think about this. We have volume, we have height. What rate is this going to be related to? Definitely not height, because that's linear. Volume. So we know that in our givens, that dv dt is equal to 12 feet cubed per minute. So it actually does work out to our benefit to analyze units. Unit analysis is something you're going to see very often with physics, but however, it works very, very well in calculus as well. So now we're going to say, how fast is the height of the sand pile changing? So the height changing. So we're thinking, okay, if it's changing, we know that it's changing with respect to time. So we're looking for the variable dh dt. When the pike meaning the height of the sand pile, is 10 feet high. So according to my diagram, the height, h, when I take that snapshot, h will be equal to 10 feet. So here's what I'm given. Here's what I'm looking for. I'm given dv dt. I know I'm looking for, and I'm not going to say h prime. I just want to say h feet here to make sure there's no confusion. So let's go ahead now and take our derivative. So we're going to have dv over dt, taking our derivative implicitly, reading left to right, will equal to 3 pi. This is just a constant. And we know we can pull our constants directly out of our derivative. So we're going to have 3 pi times the derivative of h cubed, which is going to be 3h dh over dt. So we have 3 pi times 3h times dh over dt. Working our way through, we're going to have dv dt is equal to 3 pi times 3h, which gives me 9 pi h dh dt, and that will be our derivative. We took the derivative of this volume equation with respect to time, and notice it made it a lot easier because I don't have to work in terms of a product rule here. I just can work straight through and use our power rule. So let's go see what we have and make sure we have everything we need to solve this. Notice we know dV dt, that's a check, that's a check. We're looking for dH dt, so we're going to look for that, and our h is going to be a value of 10. 9 pi is constant, so we can go ahead and solve right here for dH dt. I'm going to go ahead at this point, I'm going to divide both sides by 9 pi times h. Divide both sides by 9 pi times h. So I'm going to have dH dt is equal to dV dt divided by 9 pi times h. Plugging in, dV dt is a positive 12 feet cubed per minute. It's positive because the volume is getting larger. As we add more sand to the pile, the volume is increasing. So it is going to be a positive 12 feet cubed per minute divided by 9 times pi times h. But, oh, and this is going to be, oh, my goodness, I made a mistake here. Derivative of h cubed is going to be 3h squared. I would have recognized that with my unit, so here's my mistake. I apologize about that. H cubed of h cubed is going to be 3h squared dH dt. So I'm going to have this is going to be squared, this is going to be squared, this will be squared, and this is squared. So I apologize about that, but I missed that derivative. And I would have seen that with a units check at the end. Our h is going to be 10 feet, but we're squaring this value. Simplifying, I'm going to have 12 feet cubed per minute all over 9, oops, it would be 900, but it'll be 9 pi times 100 feet squared. These are all multiplied. Simplifying, we're going to have 12 feet cubed per minute divided by 9 times pi times 100 gives me 900 pi feet squared per, just feet squared. Just feet squared. Notice here my feet squared cancel with 2 of the feet cubed. So I'm going to have 12 over 900. I hope we can now recognize what goes in that. Both 3. So we're going to be left with 3 and 4. So we're going to have 3 goes into this 4 times. 3 goes into 900 pi 300 times. 2, 4, so 2, we're going to be this. Here we're going to have 150, bear with me, I'm getting tired. And 2 goes in this once, and then we're going to have a value of 75. That should be correct. So we realize that we're going to have 1 over 75 pi, 1 over 75 pi feet per minute. So that's going to be how the height of this conical pile is changing with respect to time. I know it looks a little nasty, but something that we could work with. Also, I could have simplified it here and made this way easier on myself. 3 would have gone to this 4 times. 3 would have gone to this 3 times. 4 would have gone this once. This would have been 25. There we go. I could have made that way easier on myself. But either way would have worked. So this is going to be the rate of change of my height of my pile with respect to time. Okay, so hopefully we are working through these and we're understanding how to do them. This will bring us on to our last question. And we're going to have a 5-foot tall woman walks at 8 feet per second towards a street light that is 20 feet above the ground. And yes, I realize if she's walking at 8 feet per second, she's flying. However, she's just a sprinter. So let's go ahead and we're going to draw a picture. So I'm going to draw a stick figure picture. So I have a street light that's 20 feet above the ground. I hope we all recognize that the street light is definitely, I can't see that very well, is definitely not changing. So we're just going to call this a value of 20 feet. And notice this woman is 5 feet tall, so she's relatively smaller. And I'm going to say that she is also not changing. We're going to take a quick snapshot, and she's going to be 5 feet. So 5 feet tall. What is the rate of change of her shadow when she's 15 feet from the street light? So hopefully we can all recognize that as this light casts upon the woman, that this will create a shadow that is going to have a distance from the person herself, from herself. So there's going to be a distance here because of the shadow. So this value right here is going to be the shadow. And this distance right here is going to be the distance from the woman to the pole itself. And I'm sure all of us have all done this at one point. We've walked and we've seen the rate of our shadow getting smaller or larger as we walking toward or away from a light source at night. But this is actually just a way for us to talk about the way it works. So let's think about this. We want to know the rate of change. So again, we're thinking derivative. We're thinking derivative of the length of our shadow. This right here is our shadow. So I'm just going to call our shadow a value of x. X exists to be from the woman to the tip of her shadow. She is just x. I mean, the shadow is just x. And we want to find the rate of change in length of the shadow. So we're going to be finding dx over dt. We are looking for the rate of change of her shadow with respect to time at the specific instance when she is 15 feet from the street light. So again, this is not permanent. This is not permanent. This is at one instance. We take a snapshot, a picture of her. So we're looking, and I'm just going to call this value y, when she is equal to y, which is 15 feet from the light pole itself. So we're going to be looking when y is equal to 15 feet. And then it asks what rate is the tip of her shadow moving. But let's go ahead and work through the first part. So let us analyze this. Notice here, I'm going to do this in red. So hopefully here we see that we have a large triangle here. And it has a degree and a right angle triangle right there. Here, I'm going to do this one in blue. We have a smaller triangle that also has a 90-degree angle. And notice these two triangles share a common angle. They share a common angle. Therefore, if we know that two triangles have two angles that are congruent, and notice congruent meaning 90 is congruent to 90, they share the same angle, so that means this angle is congruent to this angle. We know that that third angle must be congruent as well. Therefore, these are similar triangles. So since we know that these are similar triangles, we can make a ratio of the relationship of their legs and hypotenuse. So we know that from here, that this value x will relate to the entire value of the length x plus y, and that will be related to the value of the height, 5 feet, to this value of 20 feet. So we know that we have similar triangles. And I'm going to draw them out for you just so you can see them. I know that wasn't a very good depiction. So here I have the first similar triangle, which is going to be the value of x and the woman's height, which is constant at 5 feet. And then I'm going to have the larger one, which we're going to do in red. And this value is going to be 20 feet. And this distance, so I'm going to split up right here, this will be x, and this is y. So this whole distance, I hope we recognize as a value of x plus y. These angles are all congruent. They share this angle in common. They're both 90-degree triangles. Therefore, we know that third angle must also be congruent. So we know that this angle is congruent to this angle. So this is bringing back some high school geometry, the law of similar triangles. Two triangles that share two similar angles have a third angle, which also must be congruent. Therefore, there is a similar ratio between the set of their legs and hypotenuse. Whew. Okay, so let's talk about this relationship. We know that we can create the relationship x. Oops, I'll do it in black. So we know that we have the relationship x over 5. X over 5 will have to equal to x plus y all over 20. Solving, cross multiply, 20x is equal to 5x plus 5y. Subtracting 5x on both sides, we'll get 15x is equal to a value of 5y. Dividing both sides by 5, dividing both sides by 5, we get 3x is equal to a value of y. So that is going to be the relationship between the lengths and the height of these triangles, these similar triangles. Notice here, we're looking for dx over dt. So we're going to have to take the derivative of this thing with respect to time. So we're going to have 3 times dx over dt is equal to dy over dt. Okay, so we're looking for dx over dt. We know y is equal to 15 feet, but I skipped a little portion at the beginning, and it said the woman walks at 8 feet per second towards the street light. In terms of our drawing, if she's walking at 8 feet per second, 8 feet per second, that means that y is changing at the rate of 8 feet per second. She's getting closer and closer and closer. Therefore, is y getting smaller or larger? Think about this to yourself. Yes, y is getting smaller. Therefore, dy dt is actually a negative value. So dy over dt is equal to negative 8 feet per second. Because this length is changing, she's getting smaller and smaller. That is also changing her rate in a negative fashion. We also expect her shadow length to be negative as well. So notice over down here, we're going to divide both sides by 3. And I'm sorry, what are we looking for? I forgot what we're looking for. We're looking for dx dt. Yeah, so we're divide both sides by 3, divide both sides by 3. So we get dx dt is equal to dy dt. dy dt is negative 8 feet per second. Divided by 3, and this is negative, so we get negative 8/3 feet per second. So we're going to get negative 8/3, 8 feet per second. So I know a lot of times when we research this problem, or if we see something similar, people don't understand why that value is negative, but it's negative because this length is changing and becoming smaller, which means that the rate of change must be negative. So we answered the first part. Now we want to answer what rate is the tip of her shadow moving. Okay, what rate is her tip of her shadow moving? So let's go and identify the tip. The tip is just this point right here. The tip. I'm going to call that point P. Okay, let's think about this. Okay, so I realize that P is the tip of my shadow. P, if I look at P, is just going to be X plus Y. So P is equal to X plus Y. And I want to know the rate, so hopefully we're recognizing rate in terms of P, which will be dP dt is the tip of her shadow moving. I know you say, oh, it must also be 8 feet per second. However, it's not. This is a relative question. As you advance through physics, you will see that these speeds are going to be relative to the person and to the origin, and there's a bunch of factors that go into relativity. However, the value of P is not going to be the same as the speed of her walking, of her running, or in this case, speed of her sprinting. So let us take the derivative of this thing implicitly. Take the derivative of P with respect to time. We're going to have dP over dt is equal to, derivative of x is going to be dx over dt, plus the derivative of y, which is going to be dy over dt. dP dt is what we're looking for. We know dx dt, we know dy dt from up here. So all we have to do is figure it out. So dP dt is going to be equal to dx over dt, which is negative 8/3 feet per second. dy dt is negative 8 feet per second. Notice the units are the same, so we can combine their coefficients. So dP over dt is negative 30, what was that, 32, 24, 20, 32 thirds feet per second. So her shadow is actually decreasing at a faster rate than she's walking. And I know this is something little kids do all the time. They try to catch their shadow, and it never happens. And it's just it's one of these common formalities that the shadow is actually getting smaller at a faster rate. So I think that's pretty interesting. I don't know, it's something I remember doing when I was a little kid. So that answers the second part of this question. So these were the elementary questions that we can involve with related rates. Hopefully we can all answer them. So if you guys have any questions, please let me know. And I hope you guys have a great day. Cheers.